yeah, it's doing okay. Alright guys, EM induction number 2. This one we're going to be talking about generating electricity using moving magnets, moving coils, or coils and magnets moving relative to each other. We're going to talk about step up and step down transformers and where they could be used, how they might be useful, and a way to calculate the voltage on the primary or secondary based on the number of turns of wire and blah 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 on the other one. So first of all, rotating loops near magnets, or how to make a generator. So in order to make a generator we need something that moves, generally an moving magnetic field. So last video we were talking about changing magnetic flux. Here we're actually going to use it. So if we have a magnet like this one over here, and we are moving it, in and out of this loop of wire, what we're going to do is generate an EMF or a current that flows one direction, then flows the other direction. Now, if we move this in and out fast enough, far enough, the magnetic field strength is enough, there's enough loops of wire and all that sort of stuff, what we're going to be doing is generating an alternating current, so an AC, an alternating current. And the rate of change of this electric current, this alternating current, the frequency is kind of related to how quickly this moves in and out of the loop of wire. If we can automate this process, so we have a whole bunch of magnets moving near, around, or through, I guess, a whole bunch of coils of wire, what we're actually able to do is have something spin and use the spinning, so the mechanical spin, the mechanical energy that goes into spinning something around to generate the electricity. If we wire it in backwards and we use electricity to make the motion happen, that's a motor. Alright, so think about the wind towers up on the hills near Colpara, all the way through to like Crystal Brook and whatever else. What they're actually using is the wind to make a big blade spin. That big blade is attached to a stator and a bunch of motor housing electrical components, basically making a whole bunch of magnets move near a whole bunch of coils of wire. Those coils of wire are acting like the coils in the last video. They're collecting that EMF and pumping it back to the grid. Now, the EMF that's generated that we use comes out the power point at 240 volts. So it's quite a lot. We have 240 volts to play with. Now, sometimes when you're charging things like this, your phone or your laptop, you don't want all 240 because that's going to fry your poor little battery. So what we can do is use a transformer. So not the cool ones with like Autobots and stuff that I grew up with and playing with and stuff. So they have like the original Optimus Prime, like made out of metal, not plastic. It's really cool. Doesn't have any tires on it anymore though. But what we're going to be able to do is use this 240 volts, a step down transformer. So step down, and we're going to change it into, say, what are we going to make it? We're going to make it 24 volts. Just because it's going to make my maths a lot easier to do it on the fly in a sec. So what we're going to do is get 240 volts in. Now this 240 volts in is going to go into a loop like this. So remember, an alternating current is going to have the current flow in this way and out that way, and then it's going to swap and it'll flow the opposite direction. And what that does is induces a changing magnetic flux inside this green thing here, which is supposed to signify an iron core that's going through the loop of wire. So it's actually going through there and through there. Now iron is really good in that it can help sort of transport, transfer, carry, I guess, a magnetic field. You get a magnet and a bunch of paper clips. The 15th paperclip isn't magnetic, but it seems to sort of carry and hold that magnetic field within it a little bit better. So here we're going to have a changing flux. So we're going to have changing flux. So that changing flux kind of gets transported all the way over to this side. So now over this side, if we zoom in, we kind of got this idea up here. We've got a changing magnetic field, changing magnetic flux near a loop of wire. What that's going to do is induce a current. So if we have n turns of wire, we get n times the EMF out. If we have 10 turns of wire, we're going to get 10 times the 1 lot of EMF out. If we have 100, we get 100 times it. So if we have something like this, and I've actually got 10 loops of wire over here, deliberately, we're going to get 240 in our 10 loops. So this is going to generate a certain amount of magnetic flux. If we go over to the other side, I've only got 5 loops over here. So what that's going to do is, we've got 10 here, we've got 5 here. We're only able to, so this is transmitting all 10 bits of magnetic flux. This is only going to be able to pick up 5 of those. And what that means is that over here we've got half the field getting collected, I guess, compared to what was transmitted. So now what we're going to do is go and use this equation. So the voltage on the primary over the voltage on the secondary is the number of turns on the primary compared to the secondary. So if I know that I have, and I'm trying to find out what this guy's going to be. So let's do the maths now. Voltage primary over number of turns on the primary times by the number of turns on the secondary is the voltage on the secondary. So basically I have 5 compared to 10, so I have half the turns over here as I did on this side. So now I know that I can do 240 over 2, or 240 times 10 over 5 is 120, and that's the voltage on the secondary. So that's what we would pick up over here. We would pick up 120. All right. Now, if I wanted to pick up 24, I don't want to pick up 120. I only want to pick up 24. What I'm going to be able to do is change the configuration, so I can make the ratio match the ratio here. So I might have, let's say, 1,000, and this is 1/10 of that. So I'm going to have 100. So this would be the number of turns on the primary. This would be the number of turns on the secondary. And then if I had 1,000 loops here, 100 loops here, I would put 240 in, and I would get 24 out. Now, if you wanted to run your phone charger, you're going to have a different number of turns. Your phone charger is probably going on 5. I can't do 240 over 5 in my head right now. It's been a long day, but that's how many turns ratio-wise you would actually need. So 240 divided by 24 is 10, so we need a 10 to 1 ratio. Here we've got a 10 to 5, so we've got a 2 to 1 or 1 to 2 ratio, which is why we've got half the voltage out. Alright, these are very useful for your phones, so you don't blow it up. They're very useful for your laptops, so once again you don't blow that up. But it also means that you can ramp voltages up should you need to in other circumstances. All you need to do is put the primary here, secondary here. The trade-off is the electrical power that's delivered by the power point is 240 volts at 10 amps. So we've only got 2400 watts to play with. That's the amount of energy per second. We can't go over that. So if we have 1/10 of the voltage, we're going to have a trade-off with the amount of current that we're actually able to supply. Alright, so these things are super duper useful. You've probably got one at the end of your street or a few streets away. If you're on a farm, you've probably got one in the nearest stover pole. It'll look like a big metal garbage bin, and inside there'll be a whole bunch of coils of wire similar to this. The number of turns you have here compared to here tells you how big the voltage difference is. The just raw number of turns you have will kind of tell you the cleanliness, I guess, of the voltage that you get in, because the magnetic field doesn't do it perfectly. So yeah, cheap electrical components like the power supply that's powering my lights over here, yeah, it's doing okay. The one that I've got for my camera, just back there, yeah, it's a little bit shakier, I guess, with the power supply that it's putting out. It's nowhere near as clean as the battery. Anyway, yeah, I think that's all for today.